Good morning. Great to have you here. Happy Friday. Monday, student, when you come to lab, we'll turn in the equilibrium constant lab that we did this week. The Introduce Yourself lab is a full lab, so make sure you turn it in. It's really cheesy, just one page, should be pretty chill to do. Problem set 1 will be up. You won't turn that in right away. I'll put some problems on the board. I'd ask you to put your answers on the board, and we'll talk about all of them. You'll self-correct your work before turning it in. And then we'll take quiz number 1, which will have material similar probably to what you saw in the problem set. So it should be pretty chill. And we'll go next door and do the Le Chatelier's Principle Lab. So make sure you bring a printed copy of the Le Chatelier's Principle Lab. You can fill out the material as you go through. This week I gave you copies, but I won't give copies of it next week, that kind of jazz. If you have not picked your class presentation topic, try to do so by next Friday at 9 o'clock. It is worth, I think, like 5 points, so it's something to do, and it should be pretty chill. Something in science that interests you. And some topics have been claimed, but there are zillions still available, so try to find something that makes you excited. Cool. Questions? All right. On Wednesday, we left off with this example, and I went into a long spiel how the brown nitrogen dioxide gas almost killed me, and I got a little excited there, so sorry about that. But anyway, nitrogen dioxide is a brown paramagnetic and honestly pretty deadly gas. And it's in equilibrium with an invisible to our eyes, more benign gas, dinitrogen tetroxide, which is diamagnetic. It's not that you want to breathe a lot of N2O4 in, but if you have to make your choice, you want more N2O4 than NO2. This is an equilibrium. And the brown shows up right away with this color, and this gas is more colorless, so you can kind of see what's going on. Now, the equilibrium constant for this lab at room temperature is 0.0059. And if you remember from our discussion on Wednesday, the magnitude of K will tell you if you have more reactant or more product. And in this example, your K is much less than 1. Now, K will never be 0 and it will never be negative, but we are going to be concerned if it's less than 1 or more than 1. And this K is certainly less than 1. So that means we're going to have more reactant. Chemists would call this a reactant-favored reaction. And what that means is you're going to have, at equilibrium, more N2O4 than NO2. And that'll be important to us coming up here in a little bit. The equilibrium constant K, products over reactants, so it's going to be NO2 squared on the numerator divided by N2O4 in the denominator. Cool. And in this question, we have 0.50 molar N2O4 to begin with. And the question is, how much NO2 and N2O4 do we have at equilibrium? Now, it's important to remember that at equilibrium, you won't have just one or the other, like products or reactants. You're going to have both. So in this reaction, the N2O4 has to give up some of itself to make NO2. It won't go to 0, and that's the difference between Chem 221, 222, and 223. In the previous classes, we would have just assumed this went 100% over here, something like that. But not in Chem 223. This is an equilibrium. So you will have N2O4 and NO2. This number tells you you're going to have more N2O4 than NO2 at equilibrium, but overall and stuff, you're going to have some of both at the end. So to figure out how much NO2 and N2O4 you have, you'll set up the ICE table. And ICE again stands for initial change in equilibrium. And that's on the y-axis, if you will. On the x-axis, you want to put the reactants and products, and I would put them in order. Sometimes people will have like N2O4 and 2 NO2 over here. That shows the stoichiometry, and that's fantastic. And all we can tell right now is that initially we have 0.50 molar N2O4, and we don't have any NO2. So, wow, that's a great summary of this last 2 days of lecture. Any questions, this kind of stuff, before I go on? Yeah.
How would you know if you had 0 over NO2? If it obviously gives a 0.5 over N2O4.
Right. That's what you do. All right. Don't read into it. Assume that it's all N2O4 to begin with and stuff. Now, in reality, equilibrium's probably already been established, but if you put in what you think is 0.50, it should be a good place to start. So yeah. So don't read more into the problem than it gives you, kind of thing. All right. I totally know where you're coming from because I think those thoughts a lot too. Good. Okay, so got some N2O4, don't have any NO2. At equilibrium, again, everything's going to be around. We'll have more N2O4. Now, how you do this, the change part is key here. Change is really interesting, and there's two things that are important. One, N2O4 makes 2 NO2s. So change is usually represented by just X's. So you can imagine then that N2O4 will have some kind of X because there's one N2O4, and NO2 will have some kind of 2X. So the stoichiometries appear in the change line. The 1 to 2 in the balance reaction will show up down here. It's usually like X and 2X, stuff like that. But the other thing to remember is that something is going to have to decrease and something's going to have to increase. So like I said earlier, you can write like a line between reactants and products. And on one side, you're going to have something that's negative, and on the other side, you'll have something positive. And most of the time, negatives will be on the left and positives will be on the right, but sometimes it is reversed. Now in this problem, it makes sense to have a negative here because N2O4 is the only game in town, and we must make NO2. So N2O4 is going to go down by some amount X, and for every X moles of N2O4 that are used up, you're going to have twice that many, or 2X moles appearing. So again, here's that line. You can see on the left side it's negative, on the right side it's positive. And more often that's how it rolls, but you can have them reversed, and we'll see examples of these later. And the other thing, of course, is that the 1 N2O4 to 2 NO2 is shown up as 1X and 2X right there. So at equilibrium then, you'll have 0.5 minus X for N2O4, and you'll have 2X for the NO2. And these will be the parts that we'll throw into the Kc expression on the next slide. Any questions? Sweet. All right, so now that we've got those equilibrium values, we can place them in. So the NO2 was 2X on the previous slide, N2O4 was 0.5 minus X. Notice here with the stoichiometry of 2, there's like two things you do. It'll affect the X's, so you have like 2X, but you also square it. So it's a double whammer kind of thing when you have a different stoichiometry right there. But anyway, you end up then with 0.0059 equals 2X quantity squared divided by 0.5 minus X. So this part right here equals 0.0059. Now, if you've taken math before, this probably looks familiar because you've got a number and several terms with X, and you can solve these kind of problems. You want to solve for X. If you rearrange it a little bit, 2X quantity squared is 4X, and you've got to get all the X's out of the bottom, so you want to multiply both sides by 0.5 minus X. When you multiply both sides by 0.5 minus X, this part goes away, and on the left side then, you've got the K value times 0.5 minus X. Now, keeping the party going, we're going to take this number and multiply by 0.5 to get 0.0029. We're going to also take this number and multiply by minus X to get minus 0.0059X. And all of that equals 4X squared. So if you rearrange one more time, 4X squared, put all these on the other side, plus 0.0059X minus 0.0029 equals 0. And the reason that we've written it that way is because this is a quadratic equation. And I know you've all done something like this before. It may have been a while since you've done it, and that's okay too. But this is something that can definitely be solved. And I'll show you how to do the quadratic on the next slide if you haven't. I am going to take just a second, though, and advertise once again that if you happen to have the solve function on a calculator of yours, it makes mincemeat of these kind of problems. It just wipes them out. Quadratic formulas aren't hard to use, but they're a little tedious. And if you can put all this stuff in your calculator and hit the solve button, you're totally welcome to do that. Quadratics have two answers to them, and it's really important that if you do the quadratic formula with the solve function or without, make sure that you write both of your values down. All right, don't just give me the value that's actually going to be needed. That way I know that you've done the quadratic. I had a good email from one of the students, and they said, oh, solve function seems kind of like cheating, and I dig it. It does. Trust me, after you do a couple of them by hand, it's like, but it is okay. What you would do for the quadratic, if you're going to use the solve function, you would write the actual equation. You would then hit use solve function, something like that. And then again, report both x values when you get them out of your quadratic formula. So on the next slide, I'll show you how to do the quadratic formula by hand. And again, back in my day when I walked to school both uphill and going home, this is how we did it, all right? We did it the old school way. There's little songs to sing about the quadratic formula. But if you have the solve function, legit too. Any questions on any of that? Okay, so this is our quadratic equation. In the quadratic equation, there's letters that go in front of each of the coefficients. So A is usually in front of the x squared, B is usually in front of the x, and C is just the number that's by itself. And those are important for the quadratic formula we'll look at right here. So this is the quadratic formula, minus b plus or minus square root b squared minus 4ac over 2a. I say this in my sleep sometimes. I think my teachers were a little more zealous about this when I was taking it. But anyway, the a was 4, so it was 4x squared, b 0.0059x, and c minus 0.0029. And you can just literally plug this in. Now, because of the plus or minus, that's why you're going to get two values out for your x, and you should report both of them. So here's the math, all right, just a bunch of numbers. Here's minus b, plus or minus square root b squared minus 4ac over 2a. And when you break this down, do all the square root divide by 4 stuff, you end up with this. So you end up with this plus or minus 0.027, all right? And this is just the work that your calculator can do for you. Don't feel like you have to do anything crazy. When you solve for x, you get positive 0.026 and minus 0.028. And again, if you use solve or you do it by hand, you should report both values. Only one of the values, though, is going to be helpful to us in chemistry. And again, if you've been with me before, I've talked about how negative mass just doesn't fly, all right? You can't have negative grams. That means you can't have negative moles, negative molarity, all these kind of things. So if you get a negative answer, a negative x, that's not going to happen in chemistry, all right? It's a mathematical way to solve it, but it doesn't help us because you don't want to have a negative moles per liter NO2 or N2O4. So if you get a positive and a negative root, you can automatically just kill the negative one, all right? Still report it, but just don't worry about it because you can't do negative mass. So what that means then in this problem, if you have to have positive values, your x is positive 0.026 moles per liter. Now, if you remember from the first part, N2O4 was 0.50 minus x, so 0.50 minus 0.026, when you do the sig figs, is about 0.47 moles per liter. And the NO2, which was 2x, you would go 2 times this number to get 0.052. Woohoo! All right. Oh my gosh, Dr. Russell, this math is crazy. I'm not feeling very confident about it. One thing you can do, there's a couple things you can do to make yourself feel a little better about the numbers you get. And these aren't foolproof, but they can help. Earlier we saw how the K value was 0.0059 for this equilibrium. And we talked about how 0.0059 is a reactant favored K. And in this problem, that means you're going to have more N2O4 than you're going to have NO2. And if you look at the magnitudes of our answers for N2O4 versus NO2, N2O4 is quite a bit bigger. It's 0.47 versus 0.052. So this is what it means to have a reactant favored condition. You're going to have more reactant around than you have product, and that's what you see. Another thing you can do to make yourself feel a little bit better about your math if you start getting nervous is remember that this K is NO2 squared divided by N2O4. So if you take 0.052 and square it and divide it by 0.47, it should come out pretty close to 0.0059, which is the K value. So these are some ways to make you feel better. Now, when you do the squared divided by the N2O4 kind of thing, it'll be close, probably. Maybe it'll be exact, but it won't. If it's not exactly right, it's okay, because we're doing quadratics and all kinds of things. But it will make you feel maybe better if it's close. Questions? Okay. There's one more quadratic formula possibility. In this problem, we had a positive and a negative root, and you automatically kick out the negative root. No negative mass. But it's not impossible to get 2 positive roots when you do the quadratic. If you get 2 positive numbers, pick the smaller x. All right? We'll talk about this in problem set 1 next week. But if you use the smaller x, there's always going to be something minus the x or minus 2x, and it'll end up with a negative number down here in equilibrium. So again, if you get 2 positive roots for x in a quadratic, you want the smaller one. All right? The bigger one will give you a negative answer when it comes down to the equilibrium concentrations. Questions? All right. We're now going to change gears and talk about something which is also part of this chapter, but this is honestly something that's going to be helpful to us all the way through Chem 223. And this last thing we're going to talk about is called Le Chatelier's principle. Now, Le Chatelier, and I may not be doing a good job with his name, but that's what I've always been told. Le Chatelier was actually a miner. He was someone that went in and dug out minerals and stuff like that. But he did some research and thought about it, and he came up with this principle, which is really, really interesting. And it has a lot of implications for us all the way through Chem 223. Next week's lab is going to be all about Le Chatelier's principle. And what Le Chatelier kind of came up with is he realized that you can affect some chemical systems in different ways, and the changes will affect equilibrium. And the changes are usually changes to temperature, or maybe you're changing the volume, expanding or compressing, depending on what it is. Changes in pressure, so you add some other external gas or take away gas. And you can definitely change the concentrations of things. And if you change it, the chemical system reacts to kind of compensate for what you've changed. And it's a real interesting theory that works amazingly well. It's definitely kind of what I call a back of the envelope thing. It's not like something you calculate, but it does help you to understand how things have changed and why they're changing. Now, officially, Le Chatelier's principle goes like this. If a system at equilibrium is disturbed, i.e. changed, the system tends to shift its position to counter the effect of the disturbance. And let's say, as a practical example, that Kevin came down here. He's like, Russell, I'm mad at you. And he takes a swing at me. Well, I'm going to do this kind of thing, right? Because I don't want to get hit, right? And Kevin could probably knock me out. But I'm adjusting to Kevin's change, all right? And I don't think Kevin would do this, by the way. I want to make sure that's very clear. However, someone comes up to you, gets in your face, you a lot of times they'll go back like that. That's a version of Le Chatelier's principle. Like, you're just happy in equilibrium. Something happens, a fist is thrown, someone gets in your face, and you back off, right? So that's like you adjusting to the system. So in chemistry, it's not anything near as violent or as interesting, to be honest, in some ways, but you've got an equilibrium, NO2 and N2O4, whatever you've got, and something happens, like you add extra NO2 or you take away N2O4, and the reaction will adjust. Just like you step back, the reaction steps back as well. So we'll talk about here how to use Le Chatelier's principle when it comes to equilibrium, and it's a pretty amazing kind of thing. So, okay. Soft drinks, of course, have a fizz when you first open them up, like James's can right there maybe or something. And after a while, of course, it goes flat, stuff like that. But anyway, these can be described as an equilibrium. You've got CO2 that's dissolved in some kind of water base, all right, of the Coke or Monster or whatever you're drinking. And the dissolved CO2 can be liberated into CO2 gas, though it goes away, and then the water. And this reaction is actually exothermic, all right? So when you can get the CO2 and the water to go together to make dissolved CO2, you actually get some heat out, which is kind of an interesting. Let's use this example with our soft drinks to see how temperature can affect the value of K. So let's say we have this equilibrium going and we decrease the temperature, all right? Now, decreasing temperature and also increasing temperature affects the heat, okay? So here's a quick review. Exothermic reactions have heat as a product, and endothermic reactions have heat as a reactant. And if you start decreasing the temperature, all right, what that's like, it's like taking away the heat, all right? It makes the reaction colder, is one way to think about it, all right? And if the reaction gets colder, just like if you got colder, you'd put a coat on or put a blanket over you or something like that, the reaction's going to try and adjust and make itself warmer too. But instead of having a coat or a blanket, the only thing it can do is shift more reactants to products, because in the process, more heat has been created. So if you decrease the temperature, you're taking away the heat. And because the reaction gets cold, it actually shifts this reaction to the product side. Well, if you have more products and less reactants, your K value, you're going to have a bigger number here, the CO2 dissolved in water versus the pressure of CO2. Your K value is going to get bigger, all right? So on a practical level, what that means, if you cool your soft drink down, if there was gas above the water or Coke or Monster or whatever you've got, it's going to dissolve better. All right, it's going to try and chill out and the reaction is going to try and make itself warmer, and that's going to dissolve the CO2 into the water better than it was before. So decreasing the temperature is going to increase your K, because decreasing the temperature means taking away the heat. And reactants are going to make products to try and make more heat to compensate it. That's the only way the reaction can make more heat. And if you have reactants going to products, products go up, reactants go down, your K is going to be bigger. And what that also means on a practical level, cold soft drinks have more carbon dioxide dissolved. And when you take it out of the fridge and you pop the top, all right, first of all, you depressurize it, which is one thing. However, you're also warming it up. That CO2 is going to go back over here to the left. That's the sound you hear when it comes back out. So, you can use temperature changes and Le Chatelier's principle, which is what we just used, to figure out how this reaction is going to roll. And what we did with Le Chatelier, we took away the heat. The reactants are going to make more products in order to make more heat, to warm itself up. If you want to generalize it, which I would recommend, taking away something shifts the reaction to the side that you took it away. So we took away heat, the reaction shifted to the side with the heat, shifted to the product side, more products, less reactants. Now, the opposite is a good thing too, all right? So let's say we've got your soft drink and we want to increase the temperature. Increasing temperature is like adding heat. So if you get warm, you take your coat off or you take your blanket off, whatever, all right? So you want to try and get away from the heat. Reactions are the same way. You add heat, add the temperature, it makes the reaction get warm, and it tries to get away from what you're adding. So in this case, the CO2 that's dissolved is now all of a sudden going to become free CO2, a lot more of it, as you shift to the reactant side. Shifts to the reactant side mean K gets smaller. Pretty cool. So, all of this soft drink malarkey left, blah, blah, blah. Here's kind of the punchline of Le Chatelier. If you add something, add heat, the reaction tries to get away from what you add. So we added essentially a product here, to heat to the exothermic side, reaction shifted to the reactant. That's what happened when we increased the temperature. So adding, it increases to the opposite side of what you're adding. The first one, we took away heat. If you take away something, the reaction shifts to the side of what you took away. So when we cooled it off, we essentially took away heat, the reaction shifts to the side of what we took it away from. If you can see this, that you add, it moves to the opposite side, take away, it moves to the side you took something away from, you've got Le Chatelier's principle. Any questions? Okay. When you're playing with temperature, you literally are changing the value of K, all right? But the effects will still work in these next few slides. It's just that we're going to affect the relative positions of things instead of the actual value of K. Now, here's my wonderful brown, deadly, paramagnetic NO2 again in equilibrium with N2O4. This reaction is endothermic, all right? It takes heat to make this reaction happen. So in the last example, it was exothermic. Heat was a product. Here, heat is a reactant. This is the actual value of enthalpy. And if you remember from Chem 221, a little bit of Chem 222, positive delta H's mean endothermic. So that means heat's a reactant. If this delta H would have been a negative 57.2, then we would have had heat as a product down there. Okay, so like we saw earlier, the equilibrium constant will be the products, NO2 squared, divided by reactants, N2O4. And check these numbers out. Now, earlier you were using this K value, 0.0059, and that's at room temperature. This number is where water freezes, 273, and it goes from 0.0059 to 0.00077. So if you think about it going from hot to cold, all right, we are taking away the heat. And by taking away the heat, 298 to 273 is like making it colder. You're taking away this reactant. More product is moving to the reactant side. Your K value is smaller at the colder temperature than it was at the warmer temperature. So you can literally make predictions as to how K will change with temperature if you can figure out this Le Chatelier's principle thing. Now in this video, remember that the NO2 is brown and the N2O4 is colorless. So more brown means more NO2, and a lighter color brown or no color would mean N2O4.
Sealed flask, we have a mixture of dinitrogen tetroxide, a colorless gas, with the brown gas, nitrogen dioxide. When we heat the flask, however, the dinitrogen tetroxide decomposes into nitrogen dioxide, creating more of the brown gas until equilibrium is reached for the higher temperature.
What they did in this video is they talked about it as going from 273 to 298. I just told you about 298 to 273, but you can use the same idea. So at 273, the first part, you have N2O4, which is a little bit bigger molecules, and NO2s, all right? No problem. As you go from 273 to 298, you're heating it up. You're adding more heat to the reaction. Now, heat is a reactant in this endothermic reaction. And like I said, if you add heat, it's making it too hot. You want to make it colder. So the reaction is going to try and get rid of heat. So the only thing it can do is move to the product side. So notice how going from 273 to 298, the K value gets bigger, 0.00077 to 0.0059. That's an order of 10 or so. It's definitely getting bigger. Still reactant favored, but getting bigger. You're going to have more NO2 brown, more product, all right? So you can think about these things in both directions. NO2, more NO2 doesn't mean you don't have any N2O4. You're still equilibrium based. You're still going to have both. It's just that we have now more NO2 relative to N2O4 at the warmer temperature than we did at the colder temperature. Questions? All right. So again, the punchline. Let's talk about heat. You add heat, which means increase the temperature. You would make the reaction go from, in this case, reactants to products. If you make the reaction colder, it's like taking away heat. And taking away something, the reaction moves to the side that you're taking it away from. That means more reactant favor. So this is why it's really important to know if a reaction is endo or exothermic. In endothermic, this is what you see, but in exothermic, you'd see the opposite one. The K values would be bigger at the colder temperatures. At the warm, yeah, at the warm. They'd be smaller at the warm. Okay, yeah, getting myself confused. Any questions on that? Okay, so here's a question you might see. This is chlorine reacting with fluorine to make this chlorine trifluoride compound, which is pretty crazy. This compound is exothermic, so heat is being created. It's a product, all right? And the question is here, what's going to be the effect on the equilibrium if we raise the temperature? And your answers, of course, are shifts left to the reactants, shift right to the products. Those are what chemists use to describe a change to the reactor or the product side. But you can also have no change once in a while, too. All right? So first thing to ask yourself, raising the temperature, does that mean that you are adding heat or taking away heat? Adding heat, definitely. All right? Raising the temperature, add heat, taking away temperature, taking away heat. Heat in this exothermic reaction is a product, all right? So if you're adding heat, you're adding extra things to this part right here. You're making the reaction get too hot. And just like you would take your coat off to try and get away from the extra heat, the reaction's going to shift to the opposite side, trying to use up some of that heat. And if it shifts to the other side, that means you're going to have more reactants relative to products. So we would predict this would be a shift to the left. You're going to end up with more reactants and less products. If you cooled the reaction mixture down, that would be like taking away heat. That would be a shift to the product side. And again, remember, these are going to be really different depending on if they're exothermic or endothermic. So, any questions on that? Now, if you have a gas, you can also affect the pressure and the volume of the gas. This is only for gases, all right? These things don't affect the K value necessarily, but they will affect how everything works out. So again, the N2O4 is colorless, the NO2 is brown. Over here in this flask, you've got bigger N2O4s and smaller NO2s. Now, when it comes to volume and pressure changes, you have to think about the stoichiometry. And what I mean by that, in equilibrium, 1 N2O4 and 2 NO2s, all right? So if you look at this classroom right now, all right, lots of space, lots and lots of empty space, lots of distance between each one of you. But if we went to a smaller room, all right, you wouldn't have so much volume to move around with. And as the classroom got smaller and smaller and smaller, maybe we'd have to have all of you like sit in the same row next to each other or something like that, right? You can imagine. And gases are affected by these kind of things big time. If you have 2 moles, i.e. the NO2, in a flask, and you start compressing the volume, and this is actually pretty easy to do. You can transfer it to a new flask, blah, blah, blah. All right, all of a sudden the volume starts squishing together. And in an equilibrium where you can go both ways, the gas would prefer not to have 2 pieces, but to have only 1 piece. So as the volume is shrunk down, you tend to go to the side with fewer moles of gas. All right. So in this case, if you start shrinking the volume, you're going to see a shift to the side with less moles of gas. You're going to see more N2O4. On the other hand, if you have a small flask and you start expanding it to a big room or even the size of this room, now you've got lots and lots and lots of volume. And the N2O4 is like, whew, thank heavens, I can now break up into my constituent pieces and roll around and have a good time. So larger volume tends to favor more molecules, all right? So smaller volume prefers fewer gas molecules, i.e. the 1 N2O4 versus 2 NO2s. On the other hand, larger volume tends to favor more gas molecules, so 2 NO2s versus 1 N2O4. Now, volume and pressure are kind of opposite how they work. Higher pressure squishes the molecules together. And higher pressure, pressure, is going to push down to the side with fewer molecules. So higher pressure is like smaller volume. It prefers the side with fewer molecules. It's squishing them together. Remember, every mole of gas is roughly 22.4 liters or so of volume. So if you can have less volume, that's going to be good for higher pressure, all right? On the other hand, if you depressurize something, then there's less pressure forcing the molecules together. It tends to shift to the side with more molecules. So these changes are only for gases. High pressure, small volume will prefer fewer molecules. So N2O4 would be that one in this case. On the other hand, if you have bigger volumes or smaller pressure, that's going to prefer the side with more molecules, which would be 2 NO2 in this case.
Sealed flask contains 3 molecules of nitrogen dioxide for every 1 of dinitrogen tetroxide, and the system is at equilibrium. If we then transfer the mixture to a flask with a smaller volume, NO2 molecules convert to N2O4 molecules, resulting in a net decrease in the number of molecules. In this way, the system compensates for the decrease in volume by a decrease in gas pressure.
So in this case, the NO2s, they take up more volume. They start bouncing into each other. And as the volume shrinks, then they get so close, if you will, there's like a preference for making the N2O4 versus the NO2. So again, these are only for gases, all right? It's not for things that are aqueous because they don't have pressure and volume considerations. But if you have a gas, larger volume, less pressure goes to the side of more molecules. Smaller volume and higher pressure goes to the side of fewer molecules. Okay, so let's go back to the chlorine and fluorine making ClF3 example again. These are all gases, so changing pressure and volume will definitely affect things. In this problem, we're decreasing the volume, all right, so we're squishing it down. And to answer this one, whether it's left, right, or no change, you need to think about the total moles of gas. How many total moles of gas are there on the reactant side? 4. You bet. That's right. 3 plus 1 would be 4. All right. If there were solids, aqueous, liquids, ignore them. All right. You only look at the gases. 4 moles of gas. And on the product side, 2 moles of gas. So if you decrease the volume, you're squishing them together. And the reaction will shift to the side with fewer gas molecules. So in this case, we would say we'd see a shift to the right side, to the product side. 2 moles of gas will take up less volume than 3 plus 1, 4 moles of gas will. So that's why these things are affected if you have gases. Any questions? Okay. We're also going to look a little bit about just regular equilibrium when it comes to regular kind of things. This is the Haber-Fish reaction. It's used to make ammonia, and ammonia is really important for fertilizer and all kinds of fun things like that. They usually have a catalyst in there to make it be a little bit more efficient. Anyway, this K, very product favored, 3.5 times 10 to the 8 at room temperature, which is just crazy. So you have a lot more ammonia around at room temperature than you do N2 and hydrogen. So in this reaction, if you think about this Haber-Fish reaction, we can use an example of a water U-tube. Now, YouTube, usually you think of like, YouTube, the website where they have cool videos of cats doing funny things or whatever you watch on YouTube. Maybe my videos. Anyway, but we can also use the idea of how this reaction is affected in literally a water tube. Now notice here in this little animation, the left side has more water initially than the right side. And that's trying to reflect that there's 4 molecules of gas versus 2 molecules of gas. So you can think about this as a Haber-Fish reaction, and everything's at equilibrium, all right? But James is my boss, and he goes, wow, I want the maximum amount of N3 out possible. All right, that's how you're going to make the money. So we're going to pretend here that we're adding reactants or adding products, and we're also going to pretend that we're going to take away reactants and take away products to see the effect on the equilibrium. So this is kind of clever how this all works out and stuff to see. So let me show you here how this works and why it's kind of relevant to what we're doing. Now in the real world, a water U-tube like this one would be affected by gravity. You're not going to have this one higher than this one because that's where the gravity begins to mellow out. But in reality, we can use the same idea to figure out how this will change equilibrium.
When we add water to the tank on the left, the water in the tank on the right moves up, and that on the left moves down. The water moves from left to right, so we say that equilibrium shifts to the right, as it would if we added more reactants to a reversible chemical system.
Earlier I said how if you add something by Le Chatelier's, it shifts to the opposite side. And that's what we just saw on the YouTube. Like initially we added reactants, so it was up here. And what happened is the reactants were used up to make more products. So we ended up with more product at the end, like this went from there to there, something like that, upon adding reactants. And that's what happens. And in an actual water tube, you add water to the left, it's going to shift, make the right go up a little bit as it comes down. You will make more products. So again, adding reactants makes more product. Adding something to one side shifts the reaction to the opposite side. Any questions? Okay. So let's say that we add chlorine to this reaction here, the ClF3 once again. All right, adding chlorine, adding a reactant, adding something moves to the opposite side. So we would expect that it would shift to the right, making more products. Add a reactant, shifts to the products. And guess what? We're going to see in a little bit, adding a product moves to the reactants. Adding something moves to the other side.
Removing water from the left tank causes water to move from the right tank to the left. Equilibrium shifts to the left, as it does in a reversible chemical system when we reduce the quantity of the reactants.
In an actual water U-tube, if you took away some of the water from the reactant side, then the level goes down. And the system would compensate by using some of the product to make more reactants. And it's the same thing with Le Chatelier's principle. If you take away N2 or H2, the reaction's going to shift and try and make more of the chemicals that you're taking away. So taking away a reactant makes more reactants. If you take away something, Le Chatelier's principle predicts it's going to change to the side that you move from. So in this case, the water went more to this side, the products, quote unquote, on the right went to the reactants, quote unquote, on the left. Taking away something, it moves to the side you took it away from. All right, so here's another one of these. We're removing fluorine, we're removing a reactant. When you remove something, the equilibrium shifts to the side that you're taking it away from. This will be a shift to the left, to the reactant side. So hopefully you're seeing this. You add something, shifts to the opposite side of what you're adding. Take away something, reaction shifts to the side of what you're taking away.
Adding water to the right tank causes the water of the left tank to rise as water moves from the right tank to the left. Equilibrium in the system shifts to the left, as it would if we added product to a reversible reaction.
So if you add water to this side, the water goes over here to the left, so this level goes up. In the chemical world, what the analogy is if you added ammonia, all right, added the product, and the product is going to break down a little bit and make more into an H2 to reestablish equilibrium. So again, adding something, it moves to the opposite side. We added a product, reaction shifts to the left, to the reactant side. Here's another one. These are getting kind of old, I know, but here we're adding a product, ClF3, adding something moves to the other side. It's going to move to the reactant side, make more chlorine and fluorine. Chemists call this a shift to the left. Left is always reactants, right is always products in these kind of discussions. All right.
Removing water from the right tank lowers the water level of the left tank as water moves from left to right to regain an equilibrium. The equilibrium shifts to the right, as it would in a reversible chemical reaction if we subtracted product from the system.
So earlier we removed a reactant and the reaction shifted to the side where we removed it from. In this one, we've removed the product. We've removed some of the water and the water moves over this way to try and reestablish equilibrium. And that's what happens chemically. You start removing NH3, the reaction shifts to the side that you're removing from, it'll make more product. So if James is my boss and he goes, Russell, we need the maximum amount of NH3 possible, all right? Well, once equilibrium is established, I would try to add as much N2 and H2 as you can, because the more you add here, the more it's going to shift to this side. And at the same time, if it was possible, depending on chemical things, of course, I would try to remove all of the NH3 that I could as it was being made. Because as this goes down, the reaction shifts this way too. So add as much reactant as you can, take away as much product as you can. I'm getting a raise this term. Just joking, not really. I work at a community college. But anyway, the idea anyway is that, yeah, you add something, moves to the opposite side, take away, moves to the side you get away from. So in this one, if you're trying to maximize NH3, add all the reactant you can and take away all the ammonia you can as it forms. Is that cool? Questions? All right. I've got one more example that I'll show you on Monday. We're going to go back to the butane isobutane equilibrium. We'll talk about that with its equilibrium constant, but this is a great place to stop. Any last minute questions? Awesome. Have a great weekend. Thanks for being here.